Alright, what's going on, guys? So today we are going to be talking about unifying the SU2 and the U1 Legrangians. In the last video we talked about unifying them. That last video was also talking about the beginnings of what might be something looking like a W boson, and we're going to see how Z bosons come out of this unification as well. So without further ado, make sure to hit that like and subscribe button. Make sure to go into my Patreon page if you want exclusive content. Again, the exclusive content is where you'll see sort of longer, boring derivations, but we'll get to the point also in these videos so that you don't have to go to the exclusive content if you don't want to. So with that being said, let's get into the content. Okay, so recall that the U1 Lagrangian. So this is our U1 Lagrangian that we developed in the last video. And what we have here is the interaction term, okay? And you might have not come by this in the last video because this was part of the exclusive content, but this isn't really anything new. This is the interaction term, this is the potential term, and this is another potential term. This is a potential term for our spin 1 objects, potential term for our spin 1/2 objects, and this is the interaction term between the two. Okay, you can see that when you split this apart, you get what we've seen before, which is the sort of Dirac looking part, and then the interaction part as well. Okay, and then here is our SU2 Lagrangian. Our SU2 Lagrangian excuse me, is, again, we have an interaction part, takes a very similar form to this interaction part, and then we have this part right here. Okay, this part right here is the spin 1 part for the SU2 interactions, and this here, these W guys are the precluders to what we're going to be calling W bosons, but we also want to take a look at Z bosons. Z bosons are going to be a part of this game as well. The spin 1 fields that make these Lagrangians locally invariant can be summarized. So we have our B bosons. Okay, what's a B boson? Well, a B boson is just going to be these guys right here. Okay, these are the come from the electromagnetic interactions, and this was in the U1 case, right? So this was that spin 1 or that vector field in the U1 case. And instead of calling them A bosons, because this is typically A, we're just going to call them B bosons. Okay, and then we have our W bosons. This was for the SU2 case. But now we want to see how these things interact with the spin 0 fields. These are real scalar fields, okay? They can be complex, but we're going to deal just with the real case right now. So the way we're going to do this is going to be starting off with a spin 0 Lagrangian. This is what our spin 0 Lagrangian looks like. It takes the form of what looks like to be a Klein-Gordon Lagrangian. Okay, now we're going to add an extra term. Okay, this extra term, again, this is just a two interacting complex scalar fields. And what we'll so this is that extra term. We could see here also that this is interacting to scalar fields. Also, you might think, well, why are we adding this? Well, this is going to be important in helping us determine the shift in spontaneous symmetry breaking. Okay, and we'll see how that happens. All right, so now, okay, so here's spin 0, extra term, and now we have a spin coupling term. Okay, so this is that spin coupling term. And here is everything we had up here, right? So wherever we have our derivatives, essentially, we're replacing those with that covariant derivative, okay? So if there's no interaction, we can just get rid of these guys, and essentially we recover our spin 0 case. Okay, if we want to get really general, then we say we unify SU2 and U1. So this was the SU2 part. This is a U1 part. Okay. And here again is our real scalar field potential. Okay, so our real scalar field potential is being carried over everywhere here. And then we have this kinetic term, and we'll see how the Z bosons come out of this kinetic term. Okay, and that's going to be part of the exclusive content of this video, because the derivation is going to be somewhat long. So we're going to deal with this part first. What exactly is this thing going to tell us? The interaction part of our real scalar field. Well, here's that potential again. Okay, if this is a real function, in other words, it's not complex, then we can write it like this, right? So squared, it's going to be to the 4th power. This is squared, okay? Then we take the derivative of our potential with respect to phi, and we get this right here, okay? And then we can factor out a phi, okay, and we get this right here. So phi can be 0, which is a trivial case. The non-trivial case is going to be setting this part in the parentheses to 0. And because we're setting this to 0, we're finding a critical point of V, and we're calling that the minimum value of V, or the minimum value at which phi can take in order to make V critical, or in order to find that critical point, right? This is classic calculus kind of stuff. Then it's straight algebra from there, and we get to this point where the minimum value is rho squared over 2 pi and taking the square root of all of that. Not pi, sorry, 2 lambda. Now recall that these are just constants. These are just arbitrary constants for right now. But now we know that this phi min it takes on this value in terms of the constants that we put in our Lagrangian. Based off of this fact, based on the fact that we're dealing with an SU2 transformation, this must be a doublet, or a 1×2 vector essentially, right? So it has to look something like this, because again, when we are doing our SU2, I don't have to go all the way over here, but when we are doing our SU2 transformations, we want to recall that those SU2 transformations look something like this, right? Where this guy here is a matrix, making the whole thing a matrix, or a Lorentz transformation. So if the whole thing is a matrix, it's a 2×2 matrix, because this guy's 2×2. Well, that has to act on this right here, on this guy, and so this guy has to be something that can multiply with a 2×2 matrix. Okay. We're going to recall also that symmetry breaking means that one minimum is chosen, and so we say that for phi min, right, so phi min is going to take on 2 values. One of the values is going to be 0, the other one's going to be that shifted value, again, because when we look at our potential, in the case of symmetry breaking, here, I'll make this a little bit nicer looking. In the case of symmetry breaking, our potential looks like this, and this is something you can get from my quantum field theory playlist. Right. Oop, no, not. This is our potential. Right, so one of the minimums has to be chosen, while the other one not chosen. And so in order to show that, in the case of the SU, in the SU2 case, we say, okay, one is not going to be chosen, the other one is going to be chosen. Okay, and we're just going to reduce that to this, where V is equal to this. Okay, because that's just going to make things a little bit nicer to calculate. Okay, here's going to be, so now we have this, so here's our SU2 Lagrangian. We hadn't dealt with this yet, but what we did deal with was this part. This part told us that the minimum solution, this part told us what the minimum solution looked like. Okay, now we're going to turn to this part here, okay, and the solution to what we're going to see for this term is going to give, we'll give, I didn't complete this, W bosons and W and Z bosons. Okay, and we'll see exactly how that happens. I'm going to take you to the punchline here really quick, because the rest of this is going to be long and boring derivations. So what we are going to, the punchline here is going to be that we're going to get a term that looks like this. You can see two things are multiplied. This is W boson. Therefore, this is a W boson interaction. We're then going to deal with a term that looks like this. And what we're going to find is that that is going to be right here. Okay, this again looks like a mass term, and so we're going to get interaction terms for our W, or for Z bosons. Okay, and we're also going to be able to show that with all this derivation, the electromagnetic field interactions will also become recovered. So we'll have totality, right? Our Lagrangian will be complete. Okay, in the SU2 case, and then we're going to and then after this we're going to move on. We're going to talk briefly about parity violations, and we're going to talk isospin and then quarks, right? So that things are going to get very interesting from here on out. With that being said, I'm now going to get into long derivations that if you don't want to watch them, you can leave it here. If you do want to watch them, you can go onto my Patreon page, where this will be considered exclusive content. So with that being said, now I'm going to move on to the exclusive content.